So let's go then to functions of more variables. So let's start with an example from finance, from portfolio theory actually. So suppose we have two stocks, so let's call them A and B, so two shares that you can invest in. And they have certain returns, let's call those RA and RB, but of course stocks are risky and we measure that risk in terms of the variance of those returns, sigma A squared and sigma B squared. And the question now is, of course, if you can combine those two stocks in a single investment portfolio, what fraction of each of your investment should you put in each of these stocks? Now, obviously, the answer to that is going to depend on what you want, how you trade off risk basically versus return. So let's refine this question a little bit and just ask the perhaps a bit simpler question. If we combine those two stocks, A and B, in a single investment portfolio, what fractions, WA and WB, will give us the lowest or the minimum variance or the minimum risk portfolio? So should we invest say half of our money in A and half in B, or which proportion should we take? WA and WB, of course, will be fractions between 0 and 1, and they will add up to 1. So ultimately we'll add up all our investment in this 100% of the money that we want to invest in this portfolio of stocks A and B. So you can actually translate this in a math question. So if you invest away WA in stock A and the remainder WB in stock B, then of course we can compute what the variance of that portfolio is. And it turns out to be the variance of the total portfolio, where WA and WB are add up to 1 essentially, is going to be WA squared times the variance sigma squared of stock A plus WB squared times the variance of stock B. And here I'm making a silent assumption that these two stocks are actually not correlated. So if there's correlation, there will be an additional term to this expression. So the question is, can we choose this WA, this weight for stock A, and the weight WB for stock B? Can we find those weights which actually make this combined variance minimal? Or in other words, can we minimize portfolio variance? So what we're after is two weights, WA and WB, which add up to 1, so investing 100% of our capital. And each of these is going to be a value between 0 and 1, with 0 and 1 included. So perhaps we want to invest only in stock A or only in stock B, or somewhere in between. Now from this, the fact that they add up to 1, we know of course that WB will just be 1 minus WA. So in fact, we can write the variance sigma squared as a function of this WA only. So sigma squared is weight A squared times the variance sigma A squared plus weight B squared, which is nothing else than 1 minus WA squared times sigma B squared. So what is this? Well, this is a function. Sigma squared is a function of WA. Sigma A and sigma B are parameters in this function, so they're given from the outset by the problem. So we here just have a quadratic function actually of WA squared, which we want to minimize. Well, this WA itself is the domain essentially for this function, is any number between 0 and 1, 0 and 1 included. So in particular, this is a closed and a bounded interval. This function is a nice continuous function, so we can actually apply the extreme value theorem. So let's do that. So what we need to do is we want to minimize this function of WA. And how do we do this? Well, we find we use the extreme value theorem, so we will find the stationary point basically of this expression. So let me do that on paper. So we have this variance of the portfolio depends on the weight WA that you invest in stock A, and which determines then also how much we invest in stock B. So what is this variance of the total portfolio? It's variance of stock A, sigma squared A, times the weight squared invested in stock A plus the weight in stock B, which is just 1 minus WA squared, times the variance of stock B squared for these uncorrelated stocks. So we want to minimize this, so let's first of all compute the derivative. Well, first term of course it gives us 2 times WA times sigma A squared, and for the second term we can basically use the chain rule, which gives us plus minus, a minus from the internal part here, times the 2, which is exponent, times 1 minus WA sigma B squared. So here I use the chain rule. So let's rewrite it a bit. So we get 2WA sigma A squared plus 2WA sigma B squared minus 2 times 1 minus 2 times sigma B squared, right? So the minus 2 times minus WA gives me the plus 2A times sigma B squared, and the minus 2 times 1 gives me the minus 2 times sigma B squared. So we're almost there. So we have 2WA times sigma A squared plus sigma B squared minus 2 sigma B squared. So this is the derivative of the function sigma squared. If you want to minimize, so of course you can read up almost immediately what's the stationary point, so when does this vanish? Stationary point is going to be WA equals sigma B squared divided by sigma A squared sigma B squared. Now we could of course list, so one stationary point in particular, we have the 2 boundary points because WA can be 0 and 1, those are the boundaries of the domain, and we could figure out which of these values gives the highest expression for sigma squared, but we can actually take a shortcut here because we can easily note that sigma squared is actually a convex function. So if I take the derivative of sigma squared, of the derivative of the derivative, so meaning the second derivative, the second derivative of this function, if I look here, I take the derivative with respect to WA, that's going to be 2 times sigma A squared plus sigma B squared. And this is obviously bigger than 0, so this is a globally convex function. So a convex function which has a stationary point in the domain, and clearly this is going to be in between 0 and 1, so it's in the domain. That stationary point will be the global minimum. Okay, so this is the weight for the stock A that will minimize the variance of this portfolio. Okay, so let's get back to the slide then. And those same computations are actually occurring here on the slide. So we can find this weight WA, which minimizes this portfolio variance. Okay, so far so good. We know what the answer is, but typically this is not a question, but it was the question currently that we want to answer. Typically we would have more stocks, right? We don't choose between stocks A and B, but we have a whole index perhaps, or even more firms which are traded on a particular exchange that we can choose from. So we have lots of different stocks, A, B, C, all the way up to Z and perhaps even further. So if we want to answer the similar question, what portfolio weights are going to minimize our variance, we have to find lots of different weights, one for each stock that we might buy. So this question relates to optimization again, because we want to minimize something. We want to minimize the variance in this case, but now with many variables, not just WA, but also all these other weights. How should we do that? So this is just one example, of course, of a function of more variables. So the finance example I just did was portfolio optimization with many stocks. Okay, many stocks, how should I minimize perhaps the variance, or how should I maximize return given a certain variance, those sort of questions. In microeconomics, you might have a look at multi-product firms which sell 2 or 3 or perhaps even 10 different brands of products, and they want to optimize their profits by selling different quantities of the different goods into the market. And they will have to determine how large will be the quantity of each good. So that's many different X's, many different Q's, if you look at Q's as quantities, that you want to optimize over to maximize your profits. So similarly in macroeconomics, lots of different variables. So in the easiest examples, at least you have capital and labor, and you usually have even more variables that you might want to optimize over to figure out, for instance, what the equilibrium might be. And in econometrics, likewise, we often want to do, say, regressions. We want to minimize the errors, the deviations from a straight line, basically, the sum of the squared errors. And in order to do so, we'll have to fit lines. We have to compute the different regression coefficients. So again, this is figuring out the best fit by changing a number of parameters to give good fit. So all those questions involve optimization where many variables are actually involved. So what is a function of many variables? Well, let's look at a function of two variables first. So a function for which has two variables, an x and a y, and it will also have some domain. Domain will be this set of values x and y, of course, that you can input in this function. So this function will, for any set of x and y, so a number x and a number y, the function of these two variables will give back to us some value, a specified number, f of x and y, call it z perhaps. So we might call this the height of the function, where z is then the dependent variable and the x and y are the arguments of the function, or the independent variables, we sometimes would say. So as an example, so here is a coordinate system with a three-dimensional coordinate system. You see the x and the y coordinates are basically at the base of this coordinate system on the left hand side. So any number here in this plane here would be an input. So in particular, this number would be an input to the function x and the y, so x0 and the y0. And what the function would do is to give you back some height z or z0 to which this function will send this coordinate x0 and y0. And if you do this, if this function does so for many different x's and y's, so here we have a whole domain, this rectangle here might be the domain, all the allowed x and y's that are inputs on these functions, of this function, well, the function for each of these points that we choose here in this domain will give us a result, which is z value, and which we can depict in this graph as the height of this graph. So the height of the graph here computes or shows the function value for each choice of x and y as inputs to this function. So it's a function of two variables which gives back a height, a number z. So here's yet another example. So here's a more concrete example, actually, a function of some x and y. So what does it do? Well, it will have as an input an x and a y, and it will compute. So if you give me some particular x and y, so x equals 2 and y equals 1, for instance. Well, what's the function value? Well, I just plug in for any x that I see, I plug in the 2, so we see a 2 over here. And there's also an x squared over here, so we'll be minus 2 squared over here. And for each y that I encounter, I plug in this value 1 here and 1 over here. And in the end, I can then compute the function value. And for this particular function, it turns out to be 5 times e to the minus 5. And again, I can do this for any x and y that are in the domain. So here you see what the graph of this function might look like. Basically a height diagram of this function. So that's basically the introduction to what a function of more variables means. So of course the question is going to be, how can we optimize such functions, so find the maximum or the minimum of such a function? Well, that's going to involve derivatives again, but in this case when we have multiple variables, we also will have multiple derivatives, and those are called partial derivatives. So the next section, next video, will be about those partial derivatives, and once we've covered those, we can go into optimization over two variables.